You've probably seen, I mean, we all have, right? You're looking at this multi-million-dollar magazine cover.
Oh, yeah.
And the lighting is just immaculate. The celebrity looks stunning. The typography is perfectly kerned, all of that. But then your eye catches something, slightly off near the bottom left corner.
A disembodied hand.
Yes, exactly. A disembodied hand just resting on someone's shoulder, a phantom limb. Or maybe the background is this bustling city street, but the subject looks like they're, I don't know, floating 2 inches above the pavement.
Right, because the shadow is completely missing.
Because the shadow is missing. And when you look at the absolute worst, most embarrassing digital art disasters in professional media, they almost never stem from a bad color grade.
Yeah.
Or, a poor layout.
No, it's almost always a selection issue.
It's a bad selection, universally.
It really is the original sin of digital compositing. I mean, the moment a selection is flawed, every single subsequent edit, every filter, every manipulation is built on a compromised foundation.
Yeah.
And the human eye is just incredibly adept at recognizing when an object doesn't belong in its environment. We instinctively process edge lighting, depth of field.
Ambient occlusion, all that subtle stuff.
Exactly. When a digital artist fails to properly isolate an object from its original background, all those subtle environmental cues are either destroyed or they're just incorrectly transferred. And the illusion shatters instantly.
It shatters. And, well, that shattered illusion is exactly what we are learning to avoid today. Welcome to the Deep Dive, everyone. For you listening, whether you are a seasoned creative director or, maybe you're someone just stepping into a design career, today's mission is arguably the most foundational skill you can possibly develop.
Absolutely foundational.
We are exploring the absolute mastery of the selection. It is the art of telling a computer exactly where an object begins and where it ends. And to guide us, we're doing a comprehensive breakdown of the core design concepts from a really fantastic text. It's Chapter 03. Working with selections from the book Adobe Photoshop CC Classroom in a book 2018.
It is such a remarkable text to ground this discussion in.
Right.
Yeah, because it completely bypasses the abstract theory. It just forces the user into a highly practical, stress-tested scenario right away. The chapter centers entirely around a project they call the Shadowbox Collage.
It's basically an exercise in visual taxonomy. Oh, and just a quick note for you before we get our hands dirty in the pixels. There is a book link provided in the description below. You can buy the book by scanning the QR code of that link. And please follow for more technical design breakdowns and career building content.
Awesome.
So paint the picture of this Shadowbox project for us. I mean, we aren't working with a beautifully organized, multi-layered file here, are we?
Oh, not at all. No, the starting point is essentially the digital equivalent of a junk drawer just dumped onto a table.
That's a mess.
A total mess. You are provided with a single, flat, digitized canvas, and on this one layer, several completely unrelated objects are scattered chaotically.
Like what kind of objects?
So you have a textured off-white sand dollar, a really highly complex piece of burnished coral. There's a dark, smooth mussel shell, a nautilus shell resting on this weird patterned background, a small oval plate covered in tiny seashells, and just randomly, a single metal screw.
A single screw. It's a compositor's nightmare.
It really is.
But it's a perfect training ground, right? Because the end goal is to take this chaotic single-layer scan, isolate every single item, extract them from their backgrounds, and arrange them with mathematical precision inside a digital wooden frame, complete with realistic drop shadows.
Exactly, making them look like physical objects sitting in a physical box, which really forces you to confront the ultimate perceptual disconnect between human beings and computers.
Oh, that's a good way to put it. What do you mean by that?
Well, when you or I look at that canvas, our brains instantly perform really sophisticated object recognition. We see a seashell. The computer sees absolutely nothing of the sort. The computer just sees a grid of millions of tiny colored squares. It has no conceptual understanding of what a nautilus is, and it definitely doesn't inherently know where the edge of the shell stops and the background begins.
And that brings us to the most important concept in the entire chapter. Frankly, the golden rule of all digital image manipulation. The text establishes this right out of the gate. And if you internalize nothing else from this deep dive, you have to internalize this. You must first select what you want to affect.
It is an immutable law of the software. I mean, as long as a selection is active, only the pixels within the boundary of that selection can be altered. Everything outside of it is locked down. It's completely protected.
It's binary state.
An absolute binary state.
I always think of it like an automotive painter taping off a car. Like you spend hours meticulously laying down blue painter's tape and plastic sheeting over the windows, the tires.
Yeah, that's a great analogy.
You're defining the boundary of your action. You're telling the universe, hey, I am about to spray paint everywhere, but do not let a single drop touch anything outside this line. And the selection tools in our software are really just vastly more sophisticated rolls of painter's tape.
Very apt. And just like physical tape, laying it down requires intense patience. You need a strategic approach. And crucially, you need to know which specific type of tape is required for the surface you're working on.
Right, you wouldn't use high-tack duct tape on delicate paper.
Exactly.
Yeah.
And you shouldn't use a geometric marquee tool on an organic shape.
Okay, let's break down that toolkit then. Because opening the software interface for the first time can induce sheer panic. I mean, there are dozens of tools, submenus, hidden options. It's a lot.
It's overwhelming.
Very. How do we logically categorize these tools so we don't feel like we're just guessing at which one to use?
Well, the source material provides a highly effective mental model for this. It divides the selection toolkit into 4 primary types to avoid overwhelming the user. It categorizes them based on how the tool interacts with the data.
Okay, my assumption is that the first category relies on pure structural mathematics, the geometric tools.
You'd be correct. Category 1 is geometric. This includes the rectangular marquee and the elliptical marquee. These tools, they don't care about the content of your image.
They don't look at the picture at all.
Not at all. They don't look at color or contrast. They simply draw perfect mathematical boundaries, like rectangles and ovals, based on coordinate points on the grid. Oh, and this category also houses the single row and single column marquee tools,
which select exactly one horizontal or vertical line of pixels stretching infinitely across the canvas, right?
Exactly.
Those always seem so incredibly niche to me, like until I realized how vital they are for web design or creating structural grid lines. Okay, so if category 1 is strict geometry, what's the philosophy of category 2?
Category 2 relies entirely on human motor control and intent. These are the freehand selections, primarily the Lasso family.
Ah, the trusty Lasso.
Right. The standard Lasso tool traces the exact, literal path of your mouse movement, flaws and all. Then you have the polygonal lasso, which trades some of that freedom for structure. It allows you to draw straight, point-to-point lines.
And the magnetic lasso?
The magnetic lasso acts as a bridge to our next category, really. It behaves like a freehand tool, but attempts to intelligently snap to boundaries.
Okay, so we have math and we have the human hand. Category 3 is where the software starts doing the heavy lifting, I assume.
Yes, category 3 is edge-based selections. The flagship tool here is the quick selection tool. When you use this one, you're effectively painting an area, and the underlying algorithm actively analyzes the pixels.
Like it's hunting for edges.
Hunting for defined edges and contrast boundaries to wrap the selection around. It's a very active computational process.
And finally, category 4, which I imagine focuses purely on the data values of the pixels themselves.
Color-based selections. The iconic Magic Wand tool is the primary actor here. It operates on a completely different paradigm.
It just ignores the shapes.
It ignores shapes, lines, your hand movements, all of it. It simply looks at the numerical color value of the pixel you click and selects all adjacent pixels that fall within a mathematically similar color range.
So, to recap, geometric, freehand, edge-based, and color-based. 4 distinct ways to tell the computer how to group pixels. Now, before the text directs us to pick up any of these tools, it actually mandates a quick, almost hidden housekeeping step.
Restoring the default.
Yeah. It instructs the user to hold down a specific keyboard combination. It's Ctrl, Alt, and Shift on Windows, or Command Option, and Shift on a Mac while launching the application. This restores the default preferences. Why is that so important?
Well, while it might seem like a tedious bit of IT troubleshooting, it's a vital step for professional consistency. Software of this magnitude is endlessly customizable. Every tool has a memory of its last used setting.
So if someone messed with it before you got there.
Exactly. If you, or say a colleague who used the workstation before you, changed the feathering radius on a lasso, or adjusted the tolerance of the magic wand and just left it there, the tools are going to behave in wild, unpredictable ways.
It's the digital equivalent of resetting your kitchen scale to 0 before you start measuring ingredients for a complex recipe. Like if your scale starts at -10 grams, everything you bake is going to fail, and you'll spend hours wondering what you did wrong.
Precisely. Restoring defaults ensures that when the text says select the tool behaves exactly as the foundational algorithms intended.
All right, our scale is zeroed, the environment is sterile. Let's tackle the first object on our messy scanned canvas, the sand dollar. Visually, what are we dealing with here?
The sand dollar presents a very specific set of visual data. It's an off-white, roughly circular object with a highly textured surface, but crucially, it sits against a solid, dark, deeply contrasting background.
So relying on geometry would be a mistake because it's not a mathematically perfect circle, and relying on freehand would be tedious and probably inaccurate. But that stark contrast between the bright object and the dark background, that is practically screaming for an edge-based computational approach.
The text leads us directly to the quick selection tool for this exact reason. Because the difference in luminosity and color between the sand dollar and its background is so massive, the software's edge detection algorithms can easily determine where the object ends.
You just click and roughly paint over the interior of the sand dollar, and the software throws down that selection boundary. Those moving dashed lines we lovingly refer to as the marching ants.
The marching ants.
And they just miraculously snap to the outer perimeter. But I noticed a really critical detail in the text regarding this tool. Up in the options bar, there is a small, easily ignored checkbox labeled Auto Enhance.
It is constantly overlooked.
The text explicitly instructs us to turn this on. My instinct tells me that if this feature improves the tool, it should be on by default. The fact that it isn't suggests there's a hidden cost here. Is it an issue of processing power?
Your instinct is entirely correct. It comes down to the eternal software battle between speed and quality.
Okay, tell me more.
When you use the quick selection tool with Auto Enhance turned off, the algorithm does a very fast single-pass calculation. It looks for the edge, throws the boundary down, and moves on. The result is fast, but the edge can often look jagged. It can look rough or slightly blocky because it's prioritizing speed over sub-pixel accuracy.
It's just doing the quick and dirty math.
Yes. However, when you check the Auto Enhance box, you are instructing the software's engine to perform a vastly more rigorous mathematical analysis of the boundary pixels. It utilizes more advanced algorithms to calculate a truer, smoother edge.
Oh, it looks better.
Much better. It significantly reduces that harsh stair-step effect that just screams amateur digital cutout.
So it's actively doing heavier calculus behind the scenes.
And that heavier calculus demands more CPU cycles and RAM. On a massive, high-resolution image, Auto Enhance can actually introduce noticeable lag, like the brush might literally stutter as you paint.
So software developers default to the faster, less accurate setting, so a beginner on an older machine doesn't think the program is broken.
Exactly. But for a professional workflow, where the fidelity of that edge dictates the success of the entire Shadowbox solution, you absolutely want that box checked. You pay the performance tax for the superior result.
That makes perfect sense. Okay, so our sand dollar has the marching ants wrapped perfectly around it. The digital tape is locked down. We now need to physically move this object into the designated section of our Shadowbox frame, which the text labels position A.
Right.
So we select the Move tool from our toolkit. But here is where we run into a paradigm shift that genuinely terrifies people when they first learn destructive editing.
It is the brutal reality of a flattened, single-layer file.
Right, because if you are accustomed to modern digital design, you are used to the concept of layers. You build an image like a stack of transparent glass panes, you can move the text layer, and the background layer underneath it remains perfectly intact.
But the source file provided for this lesson is a single, baked-in image. Everything exists on one flat plane.
Therefore, when you place your cursor inside the selected sand dollar, click and drag it across the canvas toward the frame, you are not hovering it over the background. You are physically ripping those selected pixels out of the grid structure.
It is a completely destructive action. As you drag the sand dollar away, the space where it used to be is just completely obliterated.
And there's a hole.
A literal hole. It usually fills with your default background color, but the original visual data of that spot is permanently erased. And even more importantly, the new location where you drop the sand dollar. Those pixels are going to completely overwrite and destroy whatever was underneath them.
It forces a highly deliberate, committed mindset. You cannot casually toss elements around on a single layer file. Now, the software does offer a little bit of a grace period, right? The text points out that this destructive overwrite isn't permanently cemented into the file history until you actually drop the selection.
Meaning, as long as those marching ants are still animating, the pixels are essentially hovering in a state of quantum superposition.
I love that phrase, quantum superposition.
It's true. You can slide the sand dollar around inside the frame, nudging it left or right, testing out the placement over the drop shadow.
But once you achieve the perfect placement, you face a common beginner interface trap. How do you tell the software, I'm finished. Cement the pixels to the canvas.
The natural human inclination is to just click your mouse somewhere else on the screen, assuming the tool will let go.
Because in almost any other type of software, a word processor, a web browser clicking outside an active element deselects it.
But Photoshop's architecture stubbornly protects your active selection. If you have the Move tool selected and you click elsewhere on the canvas, nothing happens. The marching ants just keep buzzing.
You have to explicitly issue a command to drop the tape. You must go to the top menu and select deselect, or, far more efficiently, utilize the universal keyboard shortcut.
Ctrl plus D on Windows or Command plus D on a Mac.
Learning Ctrl plus D is like an initiation rite. It becomes pure muscle memory. You will execute that keystroke thousands of times over a career.
Easily.
Okay, the sand dollar is successfully committed to the canvas. Let's examine the next object in the jump drawer. This one represents a massive escalation in difficulty. It's a small, oval-shaped plate piled high with tiny seashells.
Because of the clearly defined oval shape, we transition back to the geometric category, specifically the elliptical marquee tool.
Let's pause and acknowledge a universal truth of graphic design here. Attempting to draw a mathematically perfect oval using a computer mouse to exactly match the contours of an organically photographed object is an exercise in profound psychological frustration.
It really highlights a massive flaw in human spatial reasoning when we're interacting with a digital interface.
Completely. When we see an oval plate, our human brain wants to draw a line around the perimeter, or perhaps radiate outward from the center of the plate. But the elliptical marquee tool, by default, forces you to click and drag from an imaginary top left corner of an invisible bounding box that encompasses the oval.
It's incredibly unintuitive. You are forced to guess where that invisible corner exists in empty space. You make your best guess, you click, you drag downward and diagonally, and instantly you realize your starting coordinate was off by like 20 pixels.
The oval you're drawing is the correct proportion, but it's hopelessly misaligned with the plate.
Your natural reaction is to swear, let go of the mouse button, undo the action, and try guessing the invisible starting corner all over again. It's tedious.
So tedious. But the text reveals a workflow mechanic here that fundamentally changes how you interact with the software. It is a massive revelation. The spacebar trick.
It is an incredibly elegant solution to the bounding box problem, and it saves an immense amount of physical hand strain and time.
Walk us through the physical mechanics of this technique. How does the spacebar intervene?
Okay, so you select the elliptical marquee, you make your standard flawed guess at the starting corner, click your left mouse button, and begin dragging. As the marching ants form the oval, you see it's missing the plate. Crucially, you do not let go of the left mouse button. You maintain that pressure.
You hold the failure on the screen.
Exactly. While keeping the mouse button depressed, you reach over with your other hand and press and hold the space bar. At that exact millisecond, the software intercepts the data coming from your mouse.
Wait, so my index finger is holding the mouse click and my thumb is holding the space bar.
Yes. And now, moving your mouse no longer alters the width or height of the oval. Instead, it translates the coordinates of the entire shape across the screen.
You are literally freezing the size of the hoop and just sliding the hoop itself around the canvas.
You slide the frozen oval until the top and left curves perfectly kiss the top and left edges of the physical plate in the image. Once those two sides are aligned, you release the spacebar. But remember, you are still holding the left mouse button down.
And as soon as the spacebar is released, the mouse reverts to its original function. Moving it now resumes stretching the bottom and right sides of the oval.
You drag until the bottom and right edges align. If you overshoot it, you just hold the spacebar again, slide it back, release the spacebar, and adjust the size. You can seamlessly toggle between resizing and repositioning 100 times in a single fluid gesture without ever dropping the tool.
It transforms a rigid mathematical input into a deeply tactile sculptural process. You are molding the selection around the object. It's brilliant.
It really is.
So we have our flawless oval selection hugging the plate. Now we need to transport it to section B of our Shadowbox frame. For the sand dollar, we traveled all the way over to the toolbar palette and clicked the Move tool icon. But the text introduces a modifier key here that acts as a tremendous workflow accelerator.
Keyboard shortcuts aren't just about saving time. They are about maintaining your visual focus on the canvas rather than hunting through menus. The text outlines the temporary tool switch.
If my elliptical marquee tool is currently active, and I place my cursor inside the selected plate of shells and drag, I'm only going to move the marching ants, correct. The pixels will stay behind.
Correct. The marquee tool only manipulates the selection boundary itself.
But I don't want to lose my focus to go click the Move tool, so instead I simply press and hold the Control key on Windows or the Command key on a Mac.
And the software performs a temporary tool substitution. The crosshair cursor of the marquee instantly transforms into the black arrowhead and scissors icon of the Move tool.
That visual feedback of the scissors is such a great UI design choice. It clearly communicates, if you drag now, you are cutting these pixels out.
Right.
So you hold Control, click the plate, drag it over to section B, and release the mouse. And the moment you take your finger off the Control key, your cursor instantly reverts back to the marquee tool, ready for the next object.
It creates an incredibly fast, uninterrupted workflow. Select, hold Control to move, drop, release Control, select the next item.
But let me present a scenario that every designer faces constantly. I use the curl drag trick. I drop the plate of shells into the frame, but because I'm using a mouse, which is essentially a plastic brick sliding on a desk, my hand twitches.
Oh, inevitably.
I drop the plate exactly 3 pixels too far to the left of the painted drop shadow. It's microscopic, but it ruins the illusion. Trying to grab the plate with the mouse again to correct a 3-pixel error is agonizing. The mouse almost always overcompensates and jumps 5 pixels the other way.
The mouse is an excellent macro positioning device, but it is a terrible micro-positioning tool. For sub-millimeter adjustments, the text introduces the concept of keyboard nudging.
Nudging. It sounds incredibly gentle, which is exactly what we need. How does it function?
You use the 4 directional arrow keys on your keyboard. However, the text highlights a critical operational distinction based on which tool is actively selected in your software. This distinction causes endless confusion for beginners.
Let's break that logic down clearly then.
Okay, if you still have a selection tool active like your elliptical marquee, and you tap the right arrow key, you will only nudge the selection boundary itself. The marching ants will march 1 pixel to the right, entirely abandoning the visual data of the plate.
You were just nudging the empty tape.
Exactly. But if you have the Move tool actively selected, either by clicking it in the toolbar or by holding down that Control Command modifier key we just discussed, and you tap the right arrow key, you will nudge the selection boundary AD, all the pixels contained within it.
So the entire plate of shells shifts.
Exactly, 1 pixel to the right.
1 literal pixel of movement per keystroke. It is absolute surgical precision. You can tap it into the frame with mathematical certainty, but what if 1 pixel is too granular? What if I need to move it across the frame, but I still want the rigidity of the keyboard rather than the wobbly mouse?
You introduce another modifier key. If you hold down the Shift key while pressing an arrow key, the software multiplies the movement by a factor of 10. It becomes a macro nudge. The object leaps exactly 10 pixels per keystroke.
A power nudge. So we are power nudging our plate into the shadow box, aiming for the exact center. But as I'm staring closely at the screen, trying to align the edge of the plate with the edge of the shadow, I encounter a major visual hindrance: the marching ants themselves.
They get in the way.
They really do. That animating black and white dashed line is relatively thick on the screen. It creates visual noise right at the crucial edge I am trying to align.
It's a very real optical problem. You cannot accurately judge the aesthetic placement of an object when a flashing neon sign is covering the perimeter.
But I'm caught in a trap. If I use Ctrl plus D to drop the selection so I can see the edge clearly, the pixels are permanently cemented to the layer. If I realize the placement is wrong after I drop it, I have to undo it and start the whole move over. How do I see the clean edge without committing the pixels?
The software architecture accounts for this exact dilemma. The text directs us to the View menu to manipulate what are called extras.
Extras meaning the non-destructive visual aids the software overlays on your image.
Correct. Grids, guidelines, smart guides, and crucially, selection edges. They are UI elements, not image data. By navigating to View Show and unchecking selection edges, you are instructing the software to turn off the visual representation of the marching ants.
The animating dashed line completely vanishes from the screen, but, and this is the vital part, the selection itself is still perfectly active mathematically.
The software is still fiercely protecting the unselected pixels. Your object is still floating, ready to be manipulated. You simply can no longer see the boundary line.
It strips away the UI clutter. You can stare at the naked edge of the plate, use your arrow keys to nudge it with total visual clarity, and secure the perfect alignment. Once it's placed, you can toggle the selection edges back on, or just hit Ctrl plus D to finally cement the pixels and move forward.
It's a masterclass in UI management. though it requires trusting the software's unseen mathematics, which is a big step for new user.
It really is. Okay, let's pivot to a completely different type of mathematics. The next object we need to extract from the junk drawer is the piece of coral.
The coral represents a significant conceptual roadblock because it entirely defeats the logic of the tools we have used up to this point.
If we evaluate the coral visually, we see why. It is a highly organic, chaotic object. It has dozens of intricate branches reaching out in all directions. It looks like a complex little tree. Therefore, our geometric marquees are entirely useless.
A rectangle cannot capture a branching structure.
And while our quick selection tool, the edge detection brush, is powerful, the coral presents a unique challenge. Because of how the branches cross over each other, there are dozens of tiny gaps, loops, and holes where the background shows through the interior of the coral.
Right, if you try to paint over that with a quick selection tool, the algorithm is going to struggle to define what is an outer edge versus an inner hole. It will likely bleed into the background or miss crucial interior cutouts.
However, the image presents one massive overriding advantage that we can leverage. While the physical structure of the coral is immensely complex, the color palette of the image is incredibly simple. The coral itself is a multi-toned, brownish-pink organic object, but it is resting against a completely uniform, stark, pure white background.
The contrast isn't just high, it's absolute, which introduces us to the reigning champion of Category 4, the Magic Wand tool.
The Magic Wand. It's perhaps the most culturally famous tool in the entire application, but it is deeply misunderstood. People assume it detects objects. It doesn't, right? As we established earlier, it selects pixels based strictly on mathematical color similarity.
But that raises a profound technical question. How does the software define similar? The coral isn't one flat color. It has highlights, deep shadows, and midtones.
If I click on a light pink pixel, how does the wand know to also grab the dark brown pixels in the shadow? The text points us to a specific setting in the options bar called tolerance. This concept feels like the absolute key to unlocking the magic wand.
Tolerance is the engine of the tool. To understand it, we have to look briefly at how digital color spaces are constructed. In standard 8-bit digital imaging, every single color channel, red, green, and blue, is assigned a numerical brightness value on a scale from 0 to 255. 0 represents zero light, or pure black. 255 represents maximum light, or pure white.
So every pixel has a specific 3-number coordinate on that scale.
Exactly. When you activate the magic wand and click on a single pixel in your image, the software instantly reads the exact numerical value of that specific pixel.
Let's say I click a medium pink pixel on the coral.
The wand registers that exact medium pink. Now look at the tolerance setting. The software defaults to a tolerance value of 32. This number is not arbitrary, it represents a mathematical net.
A net.
A tolerance of 32 instructs the algorithm to radiate outward from your clicked pixel and select any contiguous pixel whose color value is up to 32 numerical shades lighter or 32 numerical shades darker than the original pixel.
Oh, I see. It casts a localized net across the color spectrum.
Exactly. If you alter the tolerance to 100, the net becomes massively wider, grabbing a huge swath of contrasting tones. If you reduce the tolerance to 0, the net vanishes entirely. The wand will only select pixels that are mathematically identical to the one you clicked, down to the exact digit.
Okay, let's apply this color math to our complex coral. The coral has bright pink highlights and dark brown shadows. That range of color is vast. If I leave my tolerance at 32 and click the coral, the net isn't going to be wide enough. It might grab the midtones, but it will ignore the dark shadows and the bright highlights.
You would end up with a fragmented, patchy selection. The standard workaround is to hold the Shift key, which tells the software to add to the existing selection, and meticulously click on a dark shadow, then click on a highlight, repeatedly casting new nets until you finally capture all the varying tones of the coral.
Which is tedious, slow, and leaves a high margin for error. You might miss a tiny branch. But the text introduces a workflow strategy here that completely flips the script. It requires a philosophical inversion of how you look at an image. It's the reverse selection strategy.
It is an exercise in algorithmic efficiency. It asks the user to stop looking at the positive space, the complex coral, and look entirely at the negative space.
The background. The coral is incredibly complex in both shape and color. But the background is a vast ocean of pure, uniform, identical white pixels.
The background has a total color variation of 0. Therefore, it is infinitely easier for the computer to define and select the background than it is to select the coral.
But we don't want to move the background, we want the coral. How does the text guide us through this inversion?
It starts by having you select a tool from Category 1. You take the rectangular marquee and simply draw a large, loose box around the entire piece of coral, ensuring you capture plenty of the white background as well.
Okay, so mathematically, our active selection right now includes the complex coral AND, the white pixels immediately surrounding it.
Correct. Now you switch to the Magic Wand tool. You navigate to the Options bar at the top of the screen and locate the cluster of 4 icons that control path operations. You click the icon for Subtract from Selection.
The UI feedback confirms this by adding a tiny little minus sign next to the Magic Wand cursor.
Now, you position that minus wand over any of the pure white background pixels inside your rectangular box, and you click once.
Because the white is perfectly uniform, the Magic Wand instantly detects every single white pixel within that box. And because we are in subtraction mode, it aggressively removes every one of those white pixels from our active selection.
And what remains active?
The only thing left in the box that wasn't white, the perfectly isolated, highly complex coral. We didn't actually select the coral at all. We selected a massive block of data, and then we mathematically subtracted everything that we didn't want.
It's the sculptor's approach.
Yeah.
You start with a block of marble, and you chip away everything that doesn't look like the subject. By analyzing the data from the computer's perspective, recognizing that uniform white is easier to calculate than multi-toned pink, you arrive at a flawless selection in 2 clicks instead of 50.
It's a profound shift in thinking. The tool doesn't matter as much as the strategy behind it. Okay, the coral is extracted and moved. As we prepare to extract the next object, the dark mussel shell, the text takes an important theoretical detour. We need to talk about edge theory.
This is the invisible dividing line between an amateur composite and a professional manipulation. Up until now, we have been moving selections, but a digital selection is inherently geometric because it is built on a grid of square pixels.
Right. No matter how perfectly you trace a curve, you are still building that curve out of microscopic, rigid squares, like building a circle out of Lego bricks.
And the real world does not consist of rigid squares. Real physical objects interact with light. They have soft focus fall-off, atmospheric perspective, and microscopic edge blending. If you rip a grid of pixels out of one background and slam it onto a different background, the human eye instantly detects the harsh, stair-stepped, artificially sharp edge. It looks like a cheap sticker.
The text outlines 3 distinct computational solutions to manage edge transitions and fool the human eye: anti-aliasing, feathering, and the select and mask workspace. Let's dissect these because anti-aliasing and feathering are constantly confused by beginners. What precisely is anti-aliasing?
Anti-aliasing is an optical illusion engineered at the subpixel level. Imagine drawing a stark black diagonal line across a pure white digital canvas. Because the pixels are square, the line will look like a jagged staircase. This visual artifact is called aliasing.
The jaggies, as they used to call it in early video games.
Exactly. Anti-aliasing algorithms combat this by automatically generating a transitionary buffer of semi-transparent gray pixels along that jagged edge. By carefully mixing the black of the line with the white of the background at varying opacities, the algorithm tricks your eye into perceiving a perfectly smooth, continuous curve.
It blurs the math to create perceived smoothness.
Yes, but crucially, it does not destroy structural detail. It operates over a microscopic distance, usually just 1 or 2 pixels wide. The key operational requirement the text stresses is that for tools like the Lasso, Marquee, or Magic Wand, the anti-alias checkbox in the options bar must be checked before you make the selection. The algorithm must calculate the illusion at the exact moment the boundary is drawn. You cannot retroactively apply anti-aliasing to a hard selection.
That is a critical workflow detail. Okay, if anti-aliasing is microscopic optical illusion, how does feathering operate differently?
Feathering is a much more aggressive, macro-level manipulation of the alpha channel, the transparency of the pixels. Instead of just smoothing the microscopic staircase, feathering actively blurs the border of your selection over a defined distance.
It creates a gradient of transparency.
Exactly. If you input a feather radius of 15 pixels, the software will create a transition zone. Over the span of those 15 pixels, the object will gradually fade from 100% opaque down to 0% opaque.
Which means the edge of your cutout becomes fundamentally fuzzy.
It does cause a deliberate loss of sharp detail at the perimeter. However, when you're compositing a hard-edged object onto a complex atmospheric background, a subtle 1 or 2 pixel feather can be the exact trick needed to blend the object seamlessly into its new environment, mimicking camera focus. And unlike anti-aliasing, feathering can be applied destructively before selection. or dialed in non-destructively after a selection is made using various interface panels.
And the text briefly mentions a third option, the Select and Mask workspace.
That is an entirely separate, dedicated studio environment within the software, engineered specifically for high-end edge refinement. When anti-aliasing and simple feathering fail, for instance, when trying to extract individual strands of human hair or animal fur against a busy background, you transition into Select and Mask. It provides localized algorithmic brushes to expand, contract, smooth, and calculate complex transparencies along a boundary.
It's the heavy artillery of edge detection, but thankfully we don't need heavy artillery for our dark muscle shell. We just need to extract it.
The muscle shell presents a unique challenge that brings us to Category 2, the freehand tools.
Let's look at the data. The muscle shell is very dark. Unfortunately, the background it is resting on in the original scan is also relatively dark and heavily shadowed.
Which means the high contrast edge detection of the quick selection tool will fail. The algorithm won't be able to distinguish between the dark shell and the dark shadow. The magic wand is equally useless because the color palette is too muddy and similar to the background.
The automated math has failed us. We are forced to rely on human intervention. We have to trace the object manually using the Lasso tool.
And here we encounter another brutal reality of digital design hardware.
The computer mouse. Let me be blunt. Drawing a long, continuous, perfectly smooth curve using a computer mouse is practically impossible for the average human hand. A mouse is not a pen. It is an ergonomic block that you drag across a friction-based surface. As you try to trace the long edge of the muscle shell, your wrist catches on the desk, your hand stutters, and your perfectly smooth digital line suddenly looks like a seismograph of an earthquake.
It induces physical tension. Tracing the entire perimeter of a complex object without ever accidentally releasing the left mouse button, which would instantly close and ruin the selection, causes actual physical hand cramps.
The text provides a lifeline here, a workflow technique that is arguably the most relieving physical shortcut in the software, the Alt Option switch.
This technique bridges the gap between chaotic freehand movement and structured geometry. It allows the user to seamlessly toggle back and forth between the standard freehand lasso and the polygonal lasso without ever dropping the active selection.
Okay, let's trace this muscle shell step by step using this technique. Visually, the shell has a tightly rounded, organic curve at the bottom tip, but the long sides extending upward are relatively straight, or at least they are gentle enough arcs that they can be effectively traced using a series of short, straight lines.
You begin with the standard lasso tool. You click, hold the left mouse button down, and use your raw motor skills to slowly, carefully trace around that tight, organic bottom curve.
But as soon as I clear the curve and hit the long, straight edge of the shell, the tension in my wrist is building. I know if I keep dragging freehand, I'm going to ruin the line.
So while maintaining pressure on the left mouse button, you reach over and press and hold the Alt key on Windows or the Option key on a Mac.
And then comes the leap of faith. The text tells you to physically let go of the left mouse button.
Everything in your beginner brain screams that releasing the mouse button will finalize and ruin this selection.
But you release it, and because the Alt Option key is held down, the software halts the freehand tracking. It instantly swaps the active tool engine to the polygonal lasso. The line stops recording your hand jitters. Instead, a perfectly straight mathematical line stretches out from your last recorded point, anchoring itself to your cursor like a taut rubber band.
The physical relief is immediate. You can literally take your hand off the mouse entirely. You can flex your cramping fingers, stretch your wrist, or take a sip of coffee. As long as that Alt Option key remains depressed, the software pauses the action, waiting for your next structural command.
Once you recover, you grab the mouse again. You move the cursor further up the long edge of the shell and simply click the left button once to lay down an anchor point. You move further up, click again. You are building a structured point-to-point cage along the edge of the shell. It is vastly faster and infinitely more accurate than a freehand drag.
And when you finally reach the top of the shell, where the geometry breaks down and you need to trace another tight, organic curve,
You reverse the operational order. You press and hold the left mouse button down to re-engage the freehand engine, and then you release the Alt Option key. The rubber band vanishes, and you are instantly back to tracing the literal path of your mouse.
you toggle back and forth. Freehand for the curves, Alt-click geometry for the straights. It empowers the user to leverage the strengths of both tools simultaneously, mitigating the physical limitations of the hardware.
It is a phenomenal technique. All right, our muscle shell is perfectly lassoed. We use our chordal drag shortcut to pull it into the Shadowbox frame, specifically aiming for the section labeled D. However, we encounter a compositional orientation issue. In the original scan, the mussel shell is lying horizontally on the table, but section D of our Shadowbox is a tall, narrow, vertical slot.
We must manipulate the selected pixels geometrically. The object must be rotated.
The text directs us to the top menu, specifically Edit, Transform, Rotate.
Executing this command triggers a visual overlay. The software draws a bounding box around the extremity limits of your active selection. It's a thin wireframe rectangle adorned with small square control handles on the four corners and the midpoints of the sides.
It looks exactly like a picture frame wrapping tightly around the shell.
To execute the rotation, the text instructs you not to interact with the shell itself, but to move your cursor slightly outside the perimeter of the bounding box, near one of the corner handles.
The software reads the proximity of your cursor and alters the UI, changing your standard pointer into a small, curved, double-headed arrow. It intuitively communicates that dragging will initiate a spin.
You click and drag, and the pixels rotate around a central anchor point. However, if your goal is to make the shell perfectly mathematically vertical, relying on your visual judgment is dangerous. You might drag it to 88 degrees or 92 degrees. It will look close, but something will feel subconsciously unbalanced.
We need to enforce structural math over human error.
And the software provides a modifier key for exactly this purpose. While you're actively dragging your mouse to rotate the bounding box, you press and hold the Shift key.
The Shift key is the ultimate constraint tool.
It absolutely is. By holding Shift, you restrict the rotation engine. It will no longer spin freely. It will instantly snap the rotation to hard 15-degree increments. It snaps to 15, 30, 45, 60, and firmly locks in at a perfect mathematically true 90-degree vertical orientation.
It provides tactile feedback, almost like feeling a heavy gear click into a notch. You press the Enter key to commit the transformation, the bounding box vanishes, and the mussel shell sits perfectly upright in its slot.
It's another example of knowing when to trust your eye and when to force the algorithm to handle the precision.
Moving forward, we are blazing through this junk drawer. The next object targeted for extraction is the nautilus shell.
The Nautilus provides an excellent case study because its visual parameters sit precisely between the capabilities of the tools we've used so far.
Let's analyze the image data. The nautilus is an organic, sweeping spiral shape, so geometry fails. But unlike the mussel shell, which faded into the dark shadows, the nautilus shell is brightly lit and sits atop a heavily patterned, somewhat dark background.
The edge of the shell creates a massive, stark contrast boundary against the background.
Because of that undeniable contrast, the text introduces the final hybrid member of the Category 2 Freehand family, the magnetic lasso.
If the quick selection tool acts as an algorithmic paintbrush, the magnetic lasso acts as a computational string. It combines the human intent of a freehand path with the high contrast edge detection algorithms of Category 3.
Walk me through the mechanics of the digital string.
You position your cursor on the stark dividing line between the bright shell and the dark background. You click once to lay down the initial origin point. Then, remarkably, you release the mouse button completely. You simply move the mouse, hovering the cursor loosely along the perimeter of the shell.
You don't have to trace it perfectly, you just trace the general neighborhood of the edge.
Correct. As you move, the software acts as a real-time scanner. It analyzes the pixels within a defined radius of your cursor, searching for the highest delta of contrast. Once it identifies that steep transition between light and dark, it automatically snaps the selection line directly onto that boundary, dropping permanent anchor points, fastening points, to lock the string to the edge. It acts like a literal magnet drawn to contrast.
It is deeply satisfying to watch it work. The string just clings perfectly to the curves of the shell without requiring any real motor skill from the user. However, no algorithm is flawless. The text warns us about situations where the delta drops.
Yes, as you trace around the bottom of the Nautilus, you might encounter a patch where the shadow of the shell physically blends into a dark stripe on the background pattern. The contrast delta plummets.
The software loses the scent.
Exactly. When the algorithm cannot mathematically distinguish the edge, the magnetic string will often detach from the shell and snap wildly to a random shadow or pattern line nearby. The algorithm fails.
So how does a professional handle algorithmic failure? Does the text offer an override?
It offers two crucial interventions. First, preventative override. If you see the cursor approaching a low-contrast, muddy area, you don't wait for the algorithm to fail. You actively intervene by clicking the left mouse button manually. Each click forces the software to lay down a permanent fastening point exactly where your cursor is, overriding its contrast detection. You physically guide the string through the muddy water, and once you reach high contrast again, you stop clicking and let the magnet take over.
You're co-piloting with the AI. And what if the failure already happened? What if I drifted too far and the string snapped to the wrong shadow 3 inches behind me? Do I have to cancel the entire selection and start from the origin point?
No. The tool includes a retraction mechanic. You simply press the delete key or the backspace key on your keyboard.
And it erases the last fastening point.
It removes the most recent algorithmic anchor, and the magnetic string unstretches back to the previous point. You can tap delete multiple times, physically backing your mouse up along the path, essentially rewinding time until you reach the last accurate point on the shell. Then you use the manual click intervention to force the pass through the difficult section.
It's a beautiful dance between human intuition and machine calculation. You allow the computer to carry the burden of the tedious, obvious edges, and you forcefully take the wheel when the environment requires nuance and decision-making. Okay, the loop is closed, the Nautilus is captured, and we use our Choodle drag shortcut to deposit it into section E. We have finally reached the last object in the junk drawer, a single metallic piece of hardware, a screw.
The Shadowbox requires physical assembly, visually speaking. The project parameters demand a screw placed in all 4 corners of the wooden frame to complete the illusion.
Visually, the head of the screw is small, metallic, and most importantly, it is a perfect mathematical circle.
Which brings us full circle, pun intended, back to category 1, the elliptical marquee tool.
But wait, we spent an entire segment earlier dissecting how incredibly frustrating it is to draw circular shapes because the tool forces you to drag from an invisible top left corner bounding box. We use the spacebar trick to slide the shape into place. But for a tiny, highly specific object like a screw, even the spacebar trick feels clumsy. The text reveals a completely different operational mechanic here.
It introduces the center point method. For an object with a clearly defined physical center like the crosshead intersection on a screw, it is infinitely more logical to build the selection radiating outward from that central axis rather than guessing coordinates in empty space.
So I select the elliptical marquee. I meticulously position my crosshair cursor directly over the dead center of the Phillips head slot on the screw. I click and drag. But by default, the software still treats that central click as the top left corner. The circle balloons downward and to the right, ignoring the center.
Because you haven't given the software the override command. The text dictates that to fundamentally alter the origin logic of the tool, you must press and hold the Alt key on Windows or the Option key on a Mac simultaneously while dragging the mouse.
The Alt Option key. It's the same key we use to switch lasso modes, but here it has a completely different function.
Contextual modifiers. In the context of a geometric marquee, holding Alt Option instructs the underlying engine.
Yeah.
Do not calculate a bounding box from a corner. Calculate a radius outward from the initial click coordinate.
The selection boundary instantly alters its behavior. It blooms outward in all directions simultaneously, anchored to the center point, like dropping a stone into a pond and watching the ripples expand evenly.
Exactly. However, because you are using an elliptical tool, human error can still warp the shape. If your hand drags slightly more horizontally than vertically, you will generate an oval, not a perfect circle. A metallic screw cannot be an oval. It shatters the structural reality.
So we need our ultimate constraint tool again, the Shift key.
You layer the modifiers. You click the center, hold Alt Option to force the center point radius, and simultaneously hold Shift to force perfect one-to-one mathematical proportions.
You are holding 2 keyboard modifiers while dragging the mouse to calculate a perfect geometric expansion. It requires some finger gymnastics. It feels like playing a complex chord on a piano. But once you commit it to muscle memory, it is the absolute most efficient method for selecting radial objects.
We have our perfectly circular selection hugging the screw. We engage our curl key to turn the cursor into scissors, and we drag the screw to the bottom right corner of the wooden Shadowbox frame.
But immediately we face a major scaling issue. The original scan of the screw was taken at a much higher physical resolution than the wood texture of the Shadowbox. The screw head is massive. It looks like a hubcap sitting on a picture frame.
We must physically alter the dimensions of the selected pixel data. We need to resize.
The text sends us back to the Edit menu. Edit, Transform, Scale.
This summons the familiar bounding box with the 8 control handles. To reduce the physical footprint of the pixels, you hover over a corner handle and drag inward toward the center.
But we run into the exact same danger of distortion we faced when drawing the circle. If my hand isn't perfectly steady as I drag that corner handle, I might compress the width faster than the height. I will instantly warp my perfect circular screw into an oblong, warped mess.
The mathematical relationships must be protected. And the text reminds us that the Shift key is the universal protector of proportions.
By holding Shift while dragging that corner handle inward, the software mathematically locks the aspect ratio. The width and height must decrease by the exact same percentage simultaneously. The screw shrinks, but it remains an absolute perfect circle. We scale it down to roughly 40% of its original size until it looks proportionally correct against the wood grain. We hit Enter to commit the transformation.
So we have one perfectly sized, perfectly placed screw in the bottom right corner, but a frame requires 4 structural anchor points. We need 3 more screws.
This brings us to what might be my absolute favorite technical trick in the entire software architecture. The source text formally labels it moving and duplicating a selection simultaneously. I prefer to call it the digital cloning wand.
It is a profound workflow optimization that fundamentally bypasses standard operating system protocols.
Let's set the stage. Our Move tool is active. The tiny, perfectly scaled screw in the bottom right corner is still actively selected. The marching ants are buzzing around it. The novice approach to getting another screw would be to go up to Edit Copy, then Edit Paste, and then use the mouse to drag the new layer to the top right corner.
The novice approach works, but it is deeply inefficient on a computational level. The text introduces the modifier key workflow.
You position your cursor directly over the active selection of the screw. Then you reach down and press and hold the Alt key or the Option key on a Mac. What happens to the UI?
The software provides immediate, critical visual feedback. The standard black arrowhead cursor suddenly gains a shadow. A secondary white arrowhead appears tucked just behind the primary black one.
The double arrow. In almost all design software, that is the universal visual language indicating, I am primed to duplicate data.
While keeping the Alt Option key firmly depressed, you click your left mouse button on the screw and simply drag your mouse vertically toward the top right corner of the frame.
It is genuinely magical the first time you execute it. You are physically pulling a perfectly cloned copy of the pixels right out of the original object. The original screw remains perfectly intact in the bottom right, and a new one follows your cursor up the screen.
However, if you are attempting to build a precise architectural frame, you do not want to rely on your freehand mouse skills to align the top screw perfectly plumb with the bottom screw. A misalignment of 2 pixels will make the frame look structurally unsound.
The constraints must be enforced.
We layer our modifiers yet again. You are holding Alt to duplicate, but as you begin dragging, you also press and hold the Shift key.
As we established during rotation, Shift enforces rigid geometry. In the context of moving an object, holding Shift physically locks the trajectory of the movement. It constrains the duplicate to travel on a perfectly straight horizontal, vertical, or 45-degree diagonal axis relative to the origin point.
The cloned screw acts like it is locked onto a rigid steel rail. It slides perfectly straight up to the top right corner. You release the mouse button, and it drops flawlessly into alignment.
The efficiency is staggering. You Alt-Shift drag the top right screw straight horizontally to the top left corner. Then you Alt-Shift drag the top left screw straight vertically down to the bottom left corner. Within approximately 5 seconds, you have effortlessly cloned, perfectly aligned, and finalized all 4 hardware anchors of the Shadowbox.
Now, a critical technical listener might be pausing right now. They might be asking, why did we just spend 5 minutes analyzing a convoluted 2-finger keyboard shortcut to duplicate an object? Every computer user on Earth knows Ctrl plus C and Ctrl plus V. Why invent a new way to copy and paste? The text actually addresses this, and it provides a fascinating dive into the hidden architecture of computer memory management.
It is a phenomenal technical detail that separates power users from casual users. The difference lies in how the software interacts with the operating system's clipboard memory.
Break down the mechanics of a standard Ctrl plus C copy command.
When you execute standard copy and paste commands, the software must package all the selected pixel data, lift it completely out of the application's localized memory, and hand it over to the overarching operating system Windows or Mac-O. The OS stores that raster data in its system-wide RAM clipboard.
It exports the data to a waiting room.
Exactly. Then, when you press Ctrl plus V to paste, the software has to request that data back from the OS clipboard, import it back into the application, calculate a new mathematical layer to house it, and drop it into the dead center of your screen.
For a tiny 10-pixel screw, that transaction takes a millisecond. But what if you are working on a massive 50 megapixel raw photograph and you copy a huge chunk of high-resolution data?
You are dumping gigabytes of raster data into your system RAM. It taxes the processor, it bottlenecks your system memory, and it forces your hard drive to write massive temporary cache files. It slows the entire machine down.
Which illuminates the brilliance of the alt-drag cloning method.
The alt-drag maneuver entirely bypasses the operating system clipboard. It is a closed-loop, localized operation entirely within Photoshop's internal memory architecture. It simply points to the existing data on the canvas and duplicates it directly to a new coordinate on the same layer. It requires practically zero RAM overhead, no OS transaction, and operates instantaneously regardless of file size.
It is a masterstroke of optimized programming. Though, to be totally fair to the comprehensiveness of the source text, it does not completely dismiss standard copying protocols. It outlines them because they are structurally necessary for multi-document workflows.
Absolutely. If you need to move data from document A to document B, the alt-drag localization won't work. You must use the OS clipboard. The text details the standard copy command, but it also highlights a vital variation: copy merge.
What dictates the need for copy merged?
Standard copy only grabs data from the single layer you currently have targeted in your layers panel. If your selection boundary encompasses a complex composite built across 50 different transparent layers, standard copy will only grab the pixels from one of them. Copy merged forces the software to take a flattened WYSIWG. What you see is what you get snapshot of all visible pixels across all layers within your boundary, condensing them into a single image packet for the clipboard.
It's essentially taking a localized screenshot of your composition. And when it comes to unloading that clipboard data, the text explores options far beyond the standard Carol plus V drop in the center.
The Edit Paste special menu is a treasure trove of structural commands.
My personal favorite is Paste in Place.
An incredibly vital tool for UI designers or anyone managing strict layouts. If you cut a logo from the exact top left corner of one artboard and utilize Paste in Place on a completely different artboard, the software bypasses the center drop and calculates the exact X and Y mathematical coordinates from the origin file, pasting the logo perfectly in the top left corner of the new document.
And the text also details paste into and paste outside. These feel significantly more advanced, leaning into masking theory.
They're essentially automated compositing macros. If you draw a selection boundary, say a circle, and you execute paste into with a photograph on your clipboard, the software doesn't just drop the photo. It automatically generates a new layer, pastes the photo, and simultaneously generates a structural layer mask derived from your circular selection. The photo is instantly confined inside the circle, hiding all extraneous pixels without permanently deleting them. It is non-destructive confinement.
It's like pouring liquid metal into a predetermined mold. But for the rigid confines of our single-layer destructive Shadowbox project, bypassing the clipboard with the alt-drag clone was the most elegant, optimized solution.
Which brings us to the visual conclusion of the composition. All the disparate elements, the textured sand dollar, the complex coral, the geometric mussel, the high contrast nautilus, the plate of shells, and the 4 cloned hardware screws are perfectly extracted, meticulously placed, and arranged within the digital wooden frame occupying the top half of our canvas.
The illusion holds up. But we have a glaring issue regarding presentation. The bottom half of our canvas is now a horrific graveyard of negative space. It's filled with empty white voids and the ragged, chopped-up remnants of the original scan where we violently extracted the objects. It destroys the aesthetic of the final piece. We need to surgically remove the debris.
We enter the final phase of the project: cropping.
Now, cropping is a concept almost everyone is familiar with. We all crop photos on our smartphones to remove a photobomber or fix the composition. But the crop tool in a professional application offers a layer of philosophical choice regarding data retention that a phone app usually obscures.
When you activate the crop tool, the UI immediately wraps a robust adjustable boundary box around the absolute limits of the entire canvas.
The text draws our immediate attention to 2 highly specific settings in the options bar before we are allowed to manipulate that boundary box. The first setting dictates proportion. We must ensure the preset dropdown is set to ratio, and crucially, that the numerical value boxes next to it are completely blank.
The mathematics of aspect ratios constrain layout. If you were to type the numbers 4 and 5 into those boxes, the software engine locks the crop boundary to a strict 8:10 portrait aspect ratio. If you grab the top handle and drag it down, the software automatically forces the side handles inward to maintain the 4.5 math.
It prevents you from creating a custom shape.
Precisely. By selecting ratio and leaving the values null, you strip away the mathematical constraints. You engage a freeform crop. You can drag the top handle down to amputate the junk drawer at the bottom of the image while leaving the sides completely untouched. You can perfectly independently frame the wooden shadow box, leaving an exact, aesthetically pleasing white border around the wood.
So we drag the handles, framing the final artwork perfectly. But before we hit the Enter key to execute the cut, the text forces us to confront the second setting in the options bar. It is a single, unassuming checkbox labeled Delete Cropped Pixels.
This checkbox represents a profound structural decision about the archival nature of your file. It dictates how the software's engine handles the data existing outside your new, smaller boundary.
Walk us through the two distinct realities governed by this checkbox. What happens if I leave Delete Cropped Pixels unchecked?
If the box is unchecked, you are engaging in non-destructive data masking. When you commit the crop, the software shrinks the visible canvas to match your frame. The image looks perfect. However, the software secretly retains every single byte of data from the messy junk drawer in its memory, hiding it just beyond the visible edge of the canvas.
It just pulls the curtain over the mess.
Exactly. The benefit is supreme flexibility. If your art director looks at the file a week later and says, "We need more white space at the bottom," you can simply select the crop tool, expand the boundary downward, and the original scan data magically reappears intact.
The drawback, obviously, is file bloat. You are forcing the hard drive to store megabytes of useless, chopped-up pixel data that will never be seen in the final render.
Which brings us to the alternative. If you actively check the Delete Cropped Pixels box,
You authorize mathematical annihilation.
You do. When you execute that crop, every single pixel outside the boundary is permanently purged from the file structure. The data is destroyed, the resulting file size is vastly smaller and more efficient, but the action is irreversible once saved. There's no pulling the curtain back.
For the parameters of this specific tutorial, the text instructs us to check the box. We are committing to the composition. We execute the crop, the debris is purged, the file is saved, the Shadowbox Collage is officially complete.
It is an intensely rigorous exercise masked as a simple collage. By forcing the user through this specific sequence of objects, the text guarantees you must engage with every underlying algorithmic philosophy the selection toolkit has to offer.
Looking back over the entire workflow we just deconstructed, it is genuinely remarkable how much computational theory is hidden behind these simple tool icons. We started with the absolute binary law. You can only affect what is selected. The painter's tape analogy.
And we immediately realized that laying down that tape requires understanding the nature of the data. We used the quick selection tool, relying on its multi-pass auto-enhanced math, to hunt for stark contrast edges around the sand dollar.
We recognize the profound failure of human motor skills when trying to draw the elliptical plate, and utilize the spacebar trick to interrupt the software's coordinate system, allowing us to slide the mathematical boundary into place.
We encountered the limits of edge detection when faced with the chaotic coral, forcing us to abandon structural logic and rely entirely on the color tolerance nets of the magic wand, utilizing the reverse selection strategy to algorithmically subtract the uniform background.
We explored the microscopic optical illusion of anti-aliasing to prevent jagged edges, and used the Alt switch on the Lasso to escape the physical constraints of the computer mouse, building a rigid geometric cage around the muscle shell.
We co-piloted with the magnetic algorithm for the Nautilus, forcing fastening points when the contrast delta dropped. We altered the origin logic of the marquee to draw a circle radiating from the center of the screw.
And finally, we completely bypassed the operating system's RAM clipboard, utilizing the localized alt-drag cloning modifier to populate the frame with hardware before making a final destructive choice regarding data retention with the crop tool. It is a staggering amount of technical control.
When you synthesize all those techniques, you undergo a fundamental shift. You stop guessing at how the software might react. You transition from being a passive consumer of a user interface into an active commanding director of the underlying pixel matrix.
You learn to speak the language of the machine. And I want to use that idea to zoom out for a second and offer a final provocative thought as we wrap up this deep dive. We've spent the last hour meticulously deconstructing the highly manual, deeply physical mechanics of selecting pixels, holding modifier keys, tapping arrows, calculating color tolerance.
But if we look at the broader technological landscape right now, we are existing in an era where artificial intelligence and machine learning models are aggressively, systematically taking over design software. Modern versions of Photoshop literally feature a single button labeled Select Subject.
You click that button once. You don't hold Alt. You don't calculate tolerance. The AI model instantly analyzes the entire composition, references millions of training images to conceptually recognize that it is looking at a person or a car, and automatically wraps a nearly flawless selection boundary around the subject in less than a second.
So it raises a deeply existential question for the digital artist. In a rapidly approaching world dominated by one-click algorithmic magic, why is spending the time to master these tedious manual pixel-level tools like the spacebar trick or the polygonal lasso still considered the absolute non-negotiable hallmark of a true design professional?
It is the most critical question facing the industry today. And the answer fundamentally boils down to the concept of deterministic control versus probabilistic guessing. Artificial intelligence, despite its incredible power, is ultimately a probability engine. When you click Select Subject, the machine is making a highly educated statistical guess about what your human intent is.
But what happens when the probability engine guesses wrong? What happens when the AI analyzes the Nautilus shell, but statistically determines that the dark shadow cast by the shell is structurally part of the object itself? It wraps the marching ants around the shadow.
One-click magic sales.
Exactly. If your entire skill set is built entirely upon relying on that single AI button, your capability as a designer stops abruptly at the boundary of the algorithm's intelligence. When the machine fails. You have no recourse.
However, if you have spent the time to deeply understand the mechanics of the magic wand, the contrast thresholds of the magnetic lasso, the alpha channel physics of feathering, you inherently understand how the computer processes visual data. You aren't blindly asking a black box to perform a trick. You understand the foundational mathematics of the grid.
So when the AI inevitably grabs the shadow by mistake, the amateur throws their hands up and abandons the project. The professional simply smirks, grabs the polygonal lasso, holds down the Alt key, and forcefully manually commands the pixels into submission.
It is the difference between asking for a result and engineering a result. The computer provides the vast digital canvas and the statistical algorithms, but to achieve true, uncompromising artistic vision, you must remain the sculptor holding the chisel. Knowing exactly how, why, and where that chisel strikes the data, that is what elevates you from a software user to a designer.
Precision over probability. Ultimate creative control. Thank you so much for joining us on this incredibly exhaustive, pixel-level journey through the architecture of selections. One final reminder before we sign off. If you want to master these foundational concepts and truly take command of the software yourself, please check the description below. Scan the QR code of the link provided to buy Adobe Photoshop CC Classroom in a book 2018. It's an invaluable resource for structural learning. And please hit that follow button for more deep technical design breakdowns and career building content. Until next time, keep analyzing the edges.